Yeah. So now let us see the traversal methods. So traversal means is nothing but you're going to visit each and every node. That's all. Yeah. So there are three types of traversals. Actually, four types of travels are there. Fourth type we'll discuss it later. In order, pre-order, then post-order. In-order traversal, pre-order traversal, and post-order traversal. So like in-order traversal, the rule is first go to the left as much as possible, and then you print the current node, printing P for print, and then go to the right side. Okay, left, print, right, and here the left link and the right, left and right are all recursive calls. Okay, left and right are recursive calls. In pre-order, you just change the order. Okay. Okay. Print. First you print and then go to the left and then go to the right. In post order, do the reverse. First go to the left, then right, and then you print the data. So just remember this rule. Now we'll just try to apply this rule for in order, pre-order, and post order. So first for in order, it is left, print, and right. Okay. For each and every node. Okay. So first coming to the root node, the data is 50, right? So what the first step? You are moving to the left side. And these, with respect to this node, I'm coming to the left side. Still print and write are pending for this particular node. That we will come back because the first step itself, we are jumping to the left side. Okay. Now, once again, apply the same rule for this node. Left, root and right. Left, print and write. Okay. So first left. Then you will come to the node number 5. Okay. Now, so again from here, if you go to the left, what happens? It is none, right? It means there are further we cannot proceed for, we cannot proceed further. So what happens? You will come back to the previous node, and then the second step is write. Sorry, print. Okay. So now what happens? The first data that will get printed is 5. So with respect to this node, left is done, print is done. Now go to the right. Now coming to the right side, we have left, which is none. Okay. And then, so since it is none, you cannot go further. So next step is printing. So 10 will get printed. And then go to the right. Right is none, so we cannot proceed further. So with respect to this particular node, all the 3 steps are done. Left, print, and right are done. So go back to the previous node. In the previous node, also all the 3 steps are done. Right, left, print, and right are done. So go to the previous node. With respect to this node, only left is done, right? Still print and write are pending. So print the node. 30. Now come to the right. Okay. So on the right, left is none. So no further, you cannot move further on the left side. So print and go to the right. Right is also none, empty. So go back to the previous node. So here all 3 steps are done. Go back to the previous node. So if this node left is done, now we have to print. Now coming to the right side. Okay, because left and print are done for this node, you have to move to the right side. So now what happens here? Can anyone tell me?
So left is none.
Yeah.
So print.
Print. Yeah, very good. 75. And then
And right.
move to the right. Yeah. So coming to this node, left.
Left is 80.
Yeah. Again, from 80.
Left is none.
Left
So
is none.
80.
So print. Then
Right.
go to the right.
85.
85. Left is none. So
right. 85.
Print and then right is also none. So return back. So with respect to this node, all three are done. So return back. With respect to this node, only left is done, right? Now we have to print
90.
90 and then
Right is
right
none.
is none. So all three are done. Return back. Here also all three are done. Return back. Here also all three are done. So return to the main program from where it was called from. So this is your in-order traversal. So can you see any significance over here? Can you see something?
Ascending order.
Yes. Okay, so if you print a binary search tree in order traversal, you will get the data in ascending order. This is also another method to check whether the data got inserted properly or not. Okay, so it will be in ascending order. So now pre-order traversal. Can anyone tell me what is the pre-order traversal?
Print
Yeah,
left, right. So 50.
yes, 50.
Then left,
Hmm.
it will go to 30. Then again 55. Sorry,
Yeah, 30, and then 5,
5,
and then
10.
10. Okay,
Now
you
45.
go back, come here, and then come to the right side. So 45. Now it go back to 30, go back to 50, right side, 75. Sorry,
25. Then
left is nothing there. Right side, print 90,
90.
come to the left,
Then 85.
80, and then
80 and
85.
85. Sorry, 80 and 85.
Yeah, so this is your pre-order traversal. Now post-order traversal,
LRP. First, left and right both.
from 50, you'll go to the left. From 30, again, you go to the left. From 5, you go to the left. Okay, left is nothing. Okay, so you go to the right side,
10.
10. So from 10, you go to the left, nothing is there. Right also, nothing is there. So print 10.
10.
So now go back to 5. So with respect to 5,
5.
left is done, right is done. So print 5. So with respect to 5 also, all three are done. Go back to 30. So with respect to 30, left is done. Now go to the right.
45.
So 45, left is none, right is none. So print 45. Go back to 30, print 30.
30.
And go to 50, come to the right side, 75. Left side is done. So go to the right side. Left is
90.
80. Left is none. Go to the right.
85.
85. Left is none. Right is none. So print 85. Go back to 80. Print
80.
80. Go back to 90. Right side none. So print 90.
Mm.
Go back to 75. Print 75. Go
And then
back to 50. And print 50. Understood? So this is your in order, pre-order, and post-order traversal. Okay. So now, see, I told you these two are going to be recursive calls. Now to make recursive calls, okay, so we're not going to write method which with respect to a particular object. We're going to write it general, which means that it is going to become a class method. Class method means it is specific to the class, not specific to the object. These methods which come with self are specific to objects. Now I'm going to write a method which is without self. Without self means it is not with respect to an object. Okay. So why means recursive functions cannot be written in a normal way. So only for class methods we can do recursive functions. Okay. For that purpose only. Def in order and then I have root. See, root is here a temporary variable. Don't think that since I passed root, I change root, so the value this root is going to change. No, this is a temporary variable. So if I change this root is not going to get affected. Okay. Now, so if root is not equal to none. So why I'm writing this condition is we're going to do the three operations. Okay, three steps are going to be done only if the root is not equal to none, right? The root is none, we cannot proceed further. So for that only I'm writing if root is not equal to none. Okay. So if root is not equal to none, I just do these three operations. The first operation is move to the left. So moving to the left is nothing but changing the root to the current root's left. That's all. I mean, you're calling the in order function. You cannot call it like this. Okay, you have to call it using the class because it's a class method. Okay, bst dot in order of. Just make a note of it. Okay, root dot left child, and then print root dot data and equal to space, and then bst dot in order of root dot rl. That's all. Okay, so if the root is not equal to none, so no need to do anything, right? Okay, so it should not further proceed. That's all. So I'm just leaving it empty. If root is equal to none, nothing should happen. So this is your in order traversal. Now after inserting, let us try to print in order traversal. So how to call in order traversal? You cannot call it using the object because it is the class method. Okay, you have to call it using the class itself. Dot in order of. So I have to pass the root. So where is the root? It is nothing but bst dot root. So this might be a little difficult to understand, but so okay, fine. Let us execute this code. Okay, can you see the output? 30, 45, 50, 75, 80, and 90. Any doubts in this? Okay, just interchange the statements and write for pre-order and post-order and check whether you're getting the correct outputs. Okay, that you can do it as an assignment. Okay, fine. Now let us see, like, yeah, now we have implemented a binary search tree. Now we implemented a binary search tree. Now at the beginning itself, I told that the search complexity is going to reduce, right? If I want to search for the value 45, so if it is a normal tree, what I would do, I would search for each and every element, right? So whether this is 45, no, this is 45, no, this is 45, no, this is 45, yes. So I found the element. Like this, I would be searching for the entire list, right? Whereas here, after implementing a binary search tree, you need not look for the entire tree, right? So 45 means it should be at a particular position. So again, the search starts from the root. So first check whether root is equal to 45. No, it is not equal to 45. Then check whether the data 45 is less than the root or not. Yes, it is less than the root. So immediately go to the left. You are just skipping this entire right subtree, right? Definitely we can know that it's not present over here. Now come to the left side. It is 30. So 45 is greater than 30. So definitely it will not be present in the left side. So I can just skip the entire left subtree of 30. Just concentrate on the right side. Now we have found out 45 is equal to 45. So 45 is found. So understood how the search complexity got reduced? From n, it would be log n. Okay. If it is a complete balanced tree, then it will be log n. I'll tell you what is a balanced tree later. Any doubts in this?
No, sir.
Okay. Okay. So now let us write the code for searching. Even searching is going to be a recursive call. Okay. So what I would do, if the data is less, I'll search in the left side. Data is greater, I'll search in the right side. That's all. Okay. The link keeps on jumping. So just remember, for if you're writing any recursive method inside a class, that method should be a class method. Okay. So def search of root, comma, key. So key is nothing but the element to be searched. It is also an integer, okay? I'm just giving a different name, that's all. So the element to be searched is mentioned inside the key. Now, so like what are the stopping conditions? Okay, so there are actually two stopping conditions. Negative stopping condition and a positive stopping condition. So what is the negative stopping condition here?
It is less than the root.
No, no. Negative stopping condition. Stopping condition. See what happens if I search for,
Root is equal to
sorry Edwin. Edwin,
it's equal to
too
null.
much too much noise. Yeah, correct. This is equal to none. So if you're searching for 55, is 55 present in the tree? No, right? So that is the negative condition, negative stopping condition. If the data which you're going to search is not present in the tree, then that is negative. Then when will you know that element is not present? At some point you will reach none. Okay, so after 45, the data is 55, right? Going to search for 55. So you definitely have to move to the right side. So right side, sorry, 55 means right side here only, right? So 75 is there. So first 50, going to search for 55. So 55 is greater than 50, so move to the right. Then here it is 75. 55 is less than 75, so move to the left. So left side there are no data, which means 55 is not present. Okay, so the negative stop. See, always if you have multiple stopping conditions, look for negative condition first. Give more priority to negative condition, because if you put the positive condition, there might be a possibility that you will be searching for data in the none space. You'll be searching for data at none. Okay, fine. So here, if root is equal to none, can simply return none or return root, whatever. Okay, and then you can also print some warning message like data is not present, like that you can print over here, or you can, okay, fine, print data not found. So what is the positive stopping condition? If what? What's the positive stopping condition? If data is found, right? Is are able to hear me?
Yes, sir.
Okay.
If root is not equal to none,
No, no. I'm asking about the positive condition. If you have found the data, root dot,
equal to key.
yeah, data is equal to key,
Key.
double equal to. Okay. So if root dot data, if it's equal to key, we can just print data found, return, what we can return, or no need to return anything, just return empty return. Okay, because just data is found or not, that one alone we are going to print. So now when should we move to the left side? If
Root dot data key is less than root dot data.
yes, key is less than root dot data. Okay, move to the left side. So which is nothing but, so how to call the search function? Bst dot search of
Search.
root dot ll comma key. Okay, you can write else. Bst dot search of root dot
RS.
rl. That's all. Now if I'm searching for 45, 55, you can just write okay. So here I need to pass key. You didn't save the code. Yeah. Okay, so this is the traversal, and you have this one 45 element present, then element not present.
No.
Okay. So any doubts in this? Okay, so now let us try to understand two more functions. One is you want to count the number of elements in the given tree. Okay. The second one is you want to find the height of a given tree. So what is the height of this tree? Height is nothing but the
4.
number of levels. Okay. So 1, 2,
4.
3, 4, 5. So understood? The height of this tree is 5. And what is the count? How many number of elements are there in this tree?
10.
9, no? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 elements are there. So count is 9, height is 5. Okay. Now see actually so these are also going to be recursive functions. So again, recursion itself means you have to like visualize it properly. Okay. Now the logic is very simple. Okay. So the thing is how you're going to count is nothing but see if you are in a valid node, it means I have at least one node, right? Suppose I'm standing in a valid node, which is not none. So I have a count 1. So I take that count 1. Then what I would do is I would make a recursive call to the left side, okay, which is the responsibility of the left recursive call to count the number of elements of the left subtree and give it to me. And I'll make a right recursive call, and it is the right recursive call responsibility to give the count of the right uh, number of elements of the right subtree. So with respect to the current node, the number of nodes is nothing but number of left children or plus 1, which is nothing but the current node, plus number of right children. Understood? Any doubts in this? Number of left children plus 1 plus number of right children. This is going to be my logic. And I'm going to apply the same logic for every node. So with respect to this node also the same, right? So number of left children plus 1 plus number of right children. Even for this node, it's the same. So here the number of left children is 0 plus 1 plus number of right children is 0. So 1. So with respect to this, 0 plus 1 plus 0 is 1. So this particular node or this particular recursive call will return 1. So what happens? We have the left side 2 plus 1 plus 1, which is 4. This 4 will be returned here and it comes to the right side. Again, there are 4 nodes. This 4 will be returned here. So 4 plus 1 plus 4, which is nothing but 9. Understood?
Yes, sir.
Okay, so if you see the code, you will get shocked. Just a 2-line code. Def count of root. Okay, so if root is equal to none, return 0, right? So there are no elements at all. So return 0. Else return count of whatever I told, I'm just writing. Okay, so bst dot count of root dot left child plus 1 plus bst dot count of root dot right link. That's all. Just to make it 2 lines, I wrote it like this. Actually, it's a 4-line code. Fine. That's it. So print count is equal to bst dot count of bst dot root. Okay, how many elements are there? 1, 2, 3, 4, 5, 6 elements are there. So count should be 6. Yes. Okay. Fine. So I'll just tell you the concept for finding the height. You try to code. Yeah. Just a small modification in this count will give you the maximum. Sorry, height. Okay. So here the height is nothing but, see, suppose you take this 30. With respect to this 30, what is the height of this 30? This subtree alone. Forget about all this.
3.
3, right? Okay. So now how we're getting 3 is nothing but I am having one level over here, right? So 1 plus the maximum of the heights of left subtree and right subtree. So I have the left subtree height is 2, right subtree height is 1, right? Which is maximum? 2 is maximum. So 2 plus 1 will give me 3. That's it. Okay, this is the concept for finding the height. Okay, just try to code for height of the binary search tree. Just you can just follow this. It's a very simple. You can just have this in mind and then find the height. So next topic is deletion. Actually, it will take a lot of time to complete deletion. So let us take deletion to the next class. Okay, fine. So any doubts in how you have till this? Just have a quick revision once the class is over. Have a self revision, okay, so that you won't forget. Yes, deletion we can see it in the next class.
Okay, sir.
Any doubts?
No, sir.
Okay, fine.
Thank you, sir.
Yeah, thank you. So we can meet in the next class day after tomorrow, Saturday. Okay, thank you all.